Okay, so Bismillahirrahmanirrahim. Welcome to the class, and today we are going to start with the fifth lecture of our course. So last time, in the previous lecture, we were discussing regarding the analysis of multi-degree freedom system and the application of the modal response spectrum analysis. So we presented some steps how to extend the procedure for the analysis of real case study problem. And in this lecture, we are going to attempt an example how we actually apply those steps in the analysis of a structure. So this example is dealing with the analysis of a five-story steel frame building. So let me just write here. Okay, so I think we already mentioned the building data. Let me just write again. Okay, so as I mentioned, that this structure is a five-story frame. So let me just make a simple view of the structure. Okay, this is the elevation of the structure. So these stories, these four stories have a height of 13 feet, and the ground story has a height of 16 feet. The mass or the weight of each floor, so you mentioned here, the seismic weight, so it's 2505 kip, and on the rest of the floor it's 3132 kip. Okay, so the seismic weight on each floor typically represent the dead weight as well as a portion of the live load. So other parameters of the building, the response modification factor is given as 8, which is used to reduce the elastic forces. The risk category of this building is 2. The structure is regular. Both in elevation as well as in plane. So there are no irregularities to consider in the design. The site late long is given. This is obtained from one of the example from the United States. So if you know the site late and site long, you can obtain the geotechnical data for the design. So the site latitude is 35.29607, and the site longitude is minus 120.65306. Okay, the vibration period obtained through the dynamic modal analysis for the fundamental mode is 1.45 seconds. Okay, and the total weight, the total seismic weight of the building is 15,033 cube. Okay, now the ground motion data. The site class is D, which represents a stiff soil. Okay, so the SS, the short period spectral acceleration given as the site is 1.1 to 4G, and the spectral acceleration at vibration period 1 second is equal to 0.42 G. So these are the ground motion values which are given at the site for these lat long. Now, the USGS also provide the site amplification factor if A is 1.05 and FV is equal to 1.57. Amplification at the in the acceleration sensitive region and the amplification in the velocity sensitive region. These two will be used to convert SS and S1 to the design base values. Okay, one other thing we need to note is regarding the base shear. So the base shear of this structure is equal to 737. So using the equivalent lateral force procedure, the base shear is for this building is equal to 737. And in this current problem, we are going to use the model response spectrum analysis to calculate the base shear, and we will compare if it is less than this or if it is greater than that, and what we have to do in that case if it is less than the force calculated using the other procedure given in the code. Okay, so I'm going to teach this particular problem with the mostly with an approach of an engineer, how we do it in practice. Okay, so we're not going to do the complicated analysis of generating matrices and doing the classical eigenvalue analysis, but rather we will use computer programs how to carry out the model analysis and calculate the mode shape. Because the very first step in response spectrum analysis is to compute the mode shapes and the vibration periods of each mode. For the solution, what we need to do, compute mode shapes and vibration periods. Okay, so let me just give you this example here. Let's Okay, so these are the values obtained from the the model analysis of the same structure. So what you see in this is the deflected shape of the building for various modes from 1 to 5. And for every mode, the vibration period is given. Okay, as you see, T1 is equal to 1.45, the fundamental mode. Then it reduces to 0.53, 0.30, 0.22, and 0.16 is as we go to the higher modes. So in mode 1, if you see here, how we identify mode 1, when all the masses are moving in one direction. So that is indicating the first mode. The second mode is identified if there are some masses moving in one direction and some masses are moving in the other direction. And there is one point where the deflected shape crosses the undeflected shape once. So when you see that there is one crossing, that is the second mode. The third mode, you can see that there are masses moving in the right and left direction, and we can see that the deflected shape is crossing the undeflected shape twice. So there are two crossing points, and in the fourth mode, there are then 3 crossing points, and as you keep on going, the number of cross points, they are increasing. Okay. So this is how we can understand a given mode of a structure. So what you need to do in the first step is to carry out the model analysis of a structure in any appropriate computer program, for example, the SAP 2000 or the ATIPS or any other software. So once you obtain these model properties, mode shape, and the vibration period, the next step is that you need to normalize the values of the mode shape. These mode shape, they are the eigenvectors. So what you have to do is to normalize these deformation values at the floor. Okay? And what you have to do is to make the maximum value equal to 1 and normalize the rest of the 1. Okay? So in this, what you see, these are all normalized mode shape. Why? Because the maximum is 1. Okay, so if you see here on the on the top, you can see that this is +1 and the rest are less than that. Then there are, you can see even the same here, that it is +1 on the top and the rest, they are less than 1. And in this one, in the third case, you can see that +1 is at the first floor. And then you can see that the others are deformation, they are less than 1. So what you see here, that everywhere when you see the peak value in every mode, you make that as 1 and the rest you normalize with respect to that. Okay, so these are already normalized. So this is what you have to do. Okay, so let me just mention here. So let me mention these again here. So let's say this is the representing the level of the structure. So for the level of the structure, we have the roof, or we can say the 5th floor, then the 4th floor, 3rd, the 2nd, and then the ground floor. So for mode 1, we have a value of +1, which means we have to mention the sign because it's important for differentiating one mode from the other. So we have to mention the sign if it is positive or negative. So +1 at the roof level for mode 1, plus 0.882 here, plus 0.688 for the 3rd floor, and plus 0.501 for the 2nd floor, and plus 0.286 for the 1st floor. Similarly for mode 2, it's again plus here on the 5th floor, plus 0.43 on the fourth floor, then minus 0.594, minus 0.839, and minus 0.645 on the first floor. Now for mode 3, it's plus 0.87, 0.71, minus 0.736, minus 0.779, and plus 0.402, and plus 1 here. Okay. For mode 4, minus 0.570, plus 1, minus 0.660, minus 0.382, and plus 0.773. Okay, and for the last mode, which is mode 5, it is minus 0.126, okay, plus 0.335, minus 0.744, plus 1, and then minus 0.647. Okay, so these are the normalized modes. And for every mode, as you know, that we have the vibration period. For example, T1 is 1.45 seconds. Okay. T2 is 0.53 seconds. T3 vibration period for the third mode is 0.30 seconds. T4 is 0.22. And T5 is 0.16. Okay, so the mode shapes, they are normalized such that the target value for each mode is plus 1. This is the maximum value that we obtain at a given flow. And also, we have to keep in mind that the decimal points, these should be maintained up to 3 decimal places for each value. Okay, so once you obtain the modal properties, the mode shapes, and the vibration period, the next step is that we determine the participation factor and the participation function. Okay. So we have to determine the participation function for each mode and then sum the participation function for all modes to verify that a unity vector is created. So this will demonstrate that our calculations, they are accurate and we do not have any problem. So let's do this for the first mode. Okay, we know that the participation factor, the equation for this factor is equal to gamma is equal to the summation mi multiplied by phi, where I is equal to 1 to n, okay, and divided by the same factor mi phi, but the phi is square. And remember that the phi is a vector for mode 1. Okay, this is for mode 1. Okay, so how we can tabulate this data? Okay, so let's mention here the level. Okay, let's say this is the roof level, the fourth floor, the third floor, second, and then the first floor. Okay, so this should be the first column of the table. The second column should include the weights or the masses at every floor. We also mentioned the unit, so this is in kips. Okay, so as we know that on the roof, seismic weight is 2505, and on the rest of the floor it is 3132. Okay, so the phi value, it is dimensionless. For the first mode, it's 1.882 and all positive, 0.688 positive, 0.501, 0.286 positive. Yeah. Okay. And what we have to do, if you look at the formula, so we also have the phi square. So in this column, you take the square of the phi. Okay. So if you take the square, we will have 1 is 1. Then this becomes 0.778. This one becomes 0.473. This becomes 0.251. And this one is 0.082. Okay. Now let's multiply mi with phi so that we can get this denominator value. This will become 2505. For the fourth floor, it's 2762.4. For the next floor, it's 2154.8. For the second floor, it's 1569.1. And for the first floor, it's 895.8. Okay, and for this column, we have to calculate the mi phi square. So multiply mass with this column. Okay, so what we get is the 2505 for this, 2436.5 for the fourth floor, 1482.5, 786.1 for this, and 256.2 for the first floor. Okay, let me just do this on an Excel sheet so that we can understand the calculation. Okay, so this is the level R4321. Okay, this is the mass in kips. This is the phi value, phi square. This will be mi times phi, while this is mi times phi square. Okay, so the mass here was 2505, then 3132, and the rest are exactly the same. Phi was 1 for this case, 1882.688.501 and 0.286. Let's take the square of this. Okay, so you can see the values here. We can approximate up to the 3 decimal places. Okay, now let's calculate mi phi. So we have to multiply this column with this, and we have to multiply this column by this. Okay. Now we have to sum these two values. This one, this column, and also this column. Okay. So we got these two values. And if you look at the formula, which is here, sum of the mi phi divided by sum of the mi phi square. So this column sum divided by this column. And for this here, we just mentioned, summation that we obtain for this column is 9887.1, while this is 7466.3. Okay, so now if we put these values here in this equation, so we will get 9887.1 divided by 7466.3. Okay, so we get the factor as 1.324. Okay, so the gamma factor is equal to 1.324 for mod 1. Okay. It's this divided by this, 1.324. Okay, now we have to calculate also the participation function. So participation function we know is given as the gamma factor multiplied by the phi factor for that particular mode. So this was 1.0, 0.882, 0.688, 0.501, 0.286. Okay, so if you multiply these two, this will give you 1.324, This give you 1.168. This give you 0.911. This give you 0.663 and 0.379. Okay, so this is the participation factor. Now remember that the participation function, this one, this is the participation. Remember that the participation function is constant for a particular mode. Okay, we just mentioned that this value is always constant. If you look at the participation factor, this number depends on how you normalize the mode shape. If you do not normalize the mode shape, you will get a different factor. If you normalize them like this way, you get a different number. So this 1.324 can be different value depending how you normalize the mode shape. But the participation function remains constant, it remains unchanged, no matter what mode shape approximation or mode shape idealization you are using. If it is the originally obtained mode shape or if they are normalized, in both cases you will get the same participation function. So it's a constant value. So for the other higher modes, I will just mention the values directly. You can calculate by yourself. So you can confirm these. Okay, so participation function for mode 2. The value here is 0.44. Okay, minus 0.44 minus 0.108. Okay, plus 0.264 plus 0.373 and then plus 0.286. Okay. For the third mode, gamma 3 and phi 3, this is 0.175 minus 0.147 minus 0.156. Okay. And this is 0.081, 0.20 and 0. Okay, so these are the 5 values. For the next, gamma 4 and phi 4. Okay, this value is minus 0.064, .113, 0.075, 0.043, 0.087. Okay. Phi 5, the gamma 5 and the phi 5. This is 0.009. This is minus 0.025. This one is 0.056. 6 minus 0.075 and plus 0.048. Okay, so these are the values that you can obtain for all the modes, the participation function. Now, just to check the calculation, if so far we are accurate, so what you have to do is you to sum all these participation function and make that these gives you a unity on every floor. So let me just mention here. I will go to the Excel sheet. I go here. Okay, so for node 1, okay, let's write this here is mode 1. These are for the other 5 modes. So for mode 1, this value is 1.324, 1.168, 0.911. This is 0.663. This one is 0.379. Okay. Now for the second mode, this value is minus 0.444, minus 0.108, okay, 0.264, 0.373, and 0.286. For mode 3, 0.175, minus 0.147, minus 0.156, 0.081, and 0.200, minus 0.064, 0.113, minus 0.075, minus 0.043, 0.087, 0.009, minus 0.025, 0.056, minus 0.0775, and 0.048. So these are all the participation functions. Now let's sum them. So this is the summation. Let's sum. Okay, so if you sum all across the various modes, you get 1 here. And let's track this formula. So you get 1 also in the other floor, but these like 0.999 is also equal to 1 and 1.001 is also equal to 1. If you limit this only to 1 digit, so you can see 1 here. Okay, so this tells that our calculation is accurate. If there is any error, you will see that the participation function is not accurate, so we can revise that accordingly. Okay, so once you obtain the participation function for every mode, the next step is to determine the mass participation. So let's determine the mass. Or we can say the weight. Participation. So the effective mass in a given mode can be obtained is the summation I1 to n mi phi I, and then this is square, okay, divided by the same factor I is equal to 1 to n mi and phi I square. So if you look at this factor, it is exactly like the participation factor, but the only thing is the denominator is square. So we can use those same values, 9887.1. This is square divided by 7466.3. Okay. So the value that we get is 13,093 K. So this is the effective mass contributing to mode 1. Now how much this mass in comparison to the first to the total weight? So let's write here 13,093 divided by the total weight, which is 15033. This into 100. So if you calculate this, you will get 87.1%. Okay, which means that the first mode is contributing 87.1 mass to the to mode 1. You can also calculate the effective masses for other modes. So let me just mention here. Effective for the second mode. So I will just write the values directly. 1440 kip. In the modal mass it is contributing to the second mode is 9.6. To the total mode is 9.6. In the M effective for the third mode is 366 kip, and it is contributing is 2.4% to the total response. M effective 4 is 97 kip, and its contribution to the total mass, effective mass is 0.6%. The same is the M effective 5. It is 37 kip, and its contribution is 0.2%. If you see from these modal masses, the contribution of the modal mass reduces as we go to the higher modes. For example, it reduces from 87.1% to 9.6, 2.4, 0.6, and then 0.2. Now, remember that when we are doing modal analysis, the code proposes that we take the sufficient number of modes such that the combined modal mass becomes equal to or greater than 90%. So if we just sum the effective mass okay, so if we take the first mode mass plus the second mode, so we get 87.1 plus 9.6. the total mass becomes 96.7. Okay, so it's more than 90%. But what you can do is that you just need only to combine two modes in order to satisfy the minimum requirement of the code. That the combined modal mass in the response spectrum analysis should be equal or greater than the 90% of the total mass of the building. Okay. So once you do here, the next step is to create response spectrum. Okay, we are given the value of SS1 that we can use to convert SS and SS1 to convert them into design-based acceleration values. Now, the first thing is to understand the typical response spectrum that we use in the modal response spectrum analysis. Let me just write here. So on the x-axis, you have the value of period. Okay. On the y-axis, we have the spectral response acceleration, SAG. Okay, and the typical shape is that it starts with some value at the t0. It linearly increases to certain value, and that value is equal to SDS. SDS. Then the value remain constant for a certain range of vibration period, and after that it reduces. Okay, with the value is SD1 divided by T by SD1 divided by T. Okay, this is continued. This branch is continued. Let me just extend this till a time period that is called as TL. In the current codes of the IBC, it gives value of TL for various states in the United States, and hopefully the IBC will be also adopted soon in Pakistan as well. In UBC, this factor is not included, and this line is continued. Okay, but anyway, TL is quite a large value. It varies from 4 to 8, 12, and even up to 16 in some cases. So it's a very large value. In majority of the cases, the vibration period of the structure will be in this plateau or somewhere in this range, but always less than the TL. The vibration period for these, the start of the horizontal plateau and the corner or the ends, the end of the plateau, which are the corner periods. This is represented by TS, and this is represented by T naught. So TS is equal to SD1 divided by SDS. SDS is equal to SDS is equal to 0.79. This value is equal to 0.79. Okay, so let me just write here. SDS is 0.79. And what about SD1? SD1 is equal to 0.45. Now remember that SD1 is these are obtained from the SS and S1. So TS is calculated as 0.57. and T naught is equal to 0.2 TS. So this is 0.2, TS is 0.57, T naught is equal to 0.11 second. So that plate is start at 0.11 second up to the 0.57 second. Okay, and just for a note, so SDS, remember, is equal to 2/3 of SS and multiply by the FA. And SD1 is equal to 2/3 of S1 multiplied by FV. Okay, so once we obtain the response spectrum, so how we use this further, the next step for us is to calculate modal forces. And story share. So what we have to do, we have to calculate the modal forces in story share for all the modes. So I will just write the steps. What are the steps? Calculate modal forces and story share for all modes. So once you calculate the modal forces and story share for all the modes, the next step is to combine story shares. You have to combine the story shares of all the modes using the SRSS procedure. The square root of the sum of squares, which gives a quite good result in majority of the cases. But in case if the modal vibration periods are close to each other, in that case you have to use the CQC rule. CQC rule, the complete quadratic combination. But anyway, the SRSS gives you always, in most of the practice cases, SRSS is a fine approximation. So once you combine the story share, we have to do a reverse calculation to calculate the floor forces. Okay, so you do the reverse calculation to get the net floor forces that produces the same combined story share. Okay, we have to apply the scaling. So one scaling is that we have to divide the forces by a factor of R divided by IE, because this will convert the elastic forces into the design level forces. And also we have to, for the scaling, we have to also note the V dynamic, the base shear dynamic, base shear obtained through modal response spectrum analysis, we call them as V dynamic. It has to be equal or greater than 85% of the base shear obtained through the static procedure. Okay, so we can have this 15% of the discount on the base shear, but we should make sure that the dynamic base shear is not less than 85% of the static base shear. Okay, now let's see how we calculate the modal forces. So floor forces are obtained as A in naught, Mi, gamma n, and phi n. So this is the participation function, a given mode multiplied with the floor masses, and then multiply that with the A in naught, which is the pseudo response acceleration, okay, obtained from the design spectrum. Okay, so if you look at mode 1, in case of mode 1, the vibration period was 1.45 seconds, which is more than the TS. There was equal to 0.57 seconds, which is the corner period of the response spectrum, TS, 0.57. So T1 is greater than the TS of the design spectrum. So in that case, what we have to do, we have to use the equation of SAG, SD1 divided by T, which is equal to 0.45 divided by T. So if we put the values, what we get is 1.31 G. So this value is equal to the AN1, the AN naught, or the maximum acceleration obtained from the design spectrum for mode 1. Okay, so in case of mode 1, let me just write the forces here. So this is the roof level force in the fourth, third, second, and first floor. These forces, let me just put this in a vector, is equal to 0.31 multiplied with the mass. So look at this equation, there is A naught multiplied by Mi, and Mi is the floor masses. So 2505, 3132, 3132, 3132, 3132. Okay, and this multiplied with the participation function. So we can put that here, which is 1.324, 1.168, 0.911, 0.663, and 0.379. Okay, so if we do this calculation, we will get the forces which are equal to 1028.2, 1134, 884.5, 643.7, and 368.0. Okay, so these are the forces that you can obtain from this equation. How we obtain the story shear? So story shear from this can be obtained let me just mention here, is what you need is just to sum these forces down to the first story. So for example, 1028, you have to write the same way, 1028.2. So this is the floor force and this is the story shear. 1028.2, then plus this and this, 1134 plus 102.2 will give you 2162.2. Okay, then sum these three forces will give you 3046.7. Sum the other four, it will give you 3690.4, and then 4058.4. Okay, so this way you can obtain the story shear for every mode. Now the next step is to combine these story shear. Okay, so if you combine the story shear for all the modes, so I will just write the final value. Four, three, two, one. Okay. 1401.5, 2452.3, 3114.4, 3724.9, 422, 5.5. Okay. And this final value, this is the net base shear. Okay, so this is the base shear force, 4225.5. Okay, now what we can do is to obtain the flow forces now from this combined story shear. Let me go here. Floor forces. F roof 4, 3, 2, 1. Okay. So F roof will be equal to the base shear, which is 1.1410.5, exactly like the last value here. Okay. The next value will be obtained by subtracting this from this. Okay. So like 2452.3 minus 1401.5. Okay. And in the same way, you have to keep on subtracting the story shear, the lower story shear from the upper story shear from the lower one, from its adjacent lower one. So like 3114.4 minus 2452.3. Okay. And also 3724.9 minus 3114.4, and then 422.5 minus 3724.9. So once you subtract these, you will get the floor forces. For example, here you get 1401.5 kip, then you get 1050.8 kip. The third floor is 662.1 kip. This one is 610.5 kip and 500.6 kip. Okay, these are the floor forces that we obtained uh, from the combined story shear. And so these are the forces that will create the final mode shape envelope of the structure. So how we scale them? Now scaling of these forces. The dynamic base shear as you obtain the final base shear force was equal to 4225.5. The first thing is that we have to divide this by R over IE, where R is equal to 8 and I is equal to 1. So in this case, the force we will get is 528 kg. The dynamic base shear. Now taking the 0.85 base shear obtained through the static procedure, the ELF. So we know that the base shear was 737. So taking the 85% of this will give us 627 kg. Now the V dynamic is still less than the 627 kg. So we can see that this will govern now. Okay. Our dynamic base here should be equal to 627 at least. So what we have to do, the scaling factor, it will be equal to 627 divided by 528. Okay, so let me just calculate here. 627 divided by 528. 1.187 or 1.19 you can say. Okay. 1.19. Now you will use this factor to increase the forces. So these forces that you obtain all has to be multiplied with 1.19 in order to increase them so that the total sum is equal to 627. Okay, so once you obtain these forces, okay, the next step is that you make your own the numerical model. Okay. Sorry. Okay, let's do it again. Two, floor, 3, 4. Okay, okay. So we obtain a force here. Okay, remember one thing, that we multiply this 1.1 factor, but remember that we have to also multiply this with 1 over R over E. 1 over R divided by IE. So there is a R is equal to 8, so we have to divide all these forces by 8. That's why we get 627, which is the design level base here. So we will have a force here, then here, and then here. So this force is equal to 208. This one is 156. This one is 98, 90, and then 74. So you have to apply these forces on the structure, and you can see that the final base here that you will obtain for the structure is equal to 627. Okay? And you can design the force, design the structure member for this level of design forces. So now this is the way how you do the response spectrum analysis for the structure analysis and the design of the structure. Okay, and you can see that using this procedure can give you a discount of around 15% on the base here. And one other advantage is that because it's a dynamic and also in accordance with the actual mode shape of the structure, so it is capable to take into account the higher mode effects in the structure design. Okay, so this was all from my side. If there's anything, you can ask me. Okay, so if there's no any question, I will close, and we'll see you in the week after the next one.